recently. And of course, we also take a lot of pictures from the Space Shuttle, International Space Station as well. Let's turn our attention now to the second commercial space remote sensing system ever in operation, the first after the American Landsat system, and this is the French SPOT satellite. The French developed their competing commercial space system. It received approval in 1978 with the first launch in 1986. And the idea was to have, if you will, a comparable or competitor system to the Landsat, but designed more to European scales of land use and land holdings, which are much smaller than here in the United States. So the original SPOT system had a 10-meter panchromatic or black and white and 20-meter multispectral spatial resolution system. If you go down to that level of detail, though, you ended up with a smaller swath width of only 60 kilometers, 40 miles or so, very small swath width. It had two independent systems, so it gave a stereo viewing ability. And to date, the SPOT system has acquired almost 6 million images over the surface of the Earth. The system has continued to improve significantly over time. Now we have 2.5-meter spatial resolution data from the SPOT 5 satellite, which has been in operation since 2002. SPOT is a commercial system, but it is also partly owned by the French government. And they have a great deal of data about who uses their data for what purposes. And so it's very interesting to look at the SPOT version of what their users are using the systems for. We can see here that, again, mapping, cartography is the largest remote sensing market by far. It's amazing to think, but much of the world is still very poorly mapped. Very little of Africa. Much of the developing world is very poorly mapped at perhaps a 1 to 50,000 or 1 to 25,000 scale. So basic cartography and mapping is still the largest market in space remote sensing. Vegetation studies, forestry, agriculture, etc. Would be next. Geology third, and then sort of everything else lumped together in between. The French's SPOT system is developed by CNES, the French Space Agency, launched by the European Space Agency launchers. And as I mentioned, it is a commercial operation, but it is also partly subsidized by the French government, which is a part owner in the system. Let's take a look at what the SPOT satellite system looks like. Here's one of the earlier spots on the left before launch. So you have some people there working on the system to give a sense of the size and scale of this satellite system. Up here at the top are the two imaging devices, the two exactly similar paired imaging devices. And on the right, you can see a little diagram of the development of the system. SPOT 1 launched in early '86 and up to SPOT 5, which is in operation right now, launched in 2002. The SPOT systems are in that polar sun-synchronous orbit, 822 kilometers, a 98-degree inclination, 100-minute period, so they circle the Earth every 101 minutes. And this gives it a 26-day repeat cycle. So it goes over the same place on the Earth every 26 days. Now that's not a good repeat cycle. That's not really enough, because when you factor in cloud cover, we want to be able to acquire more passes than that, more than once every 26 days. It's a trade-off. They wanted the higher spatial resolution. In order to get that, they had smaller swath width. That means you can't see the same place very often. But the French had a very good, interesting answer to this problem. What they did is they developed their satellites with a steerable mirror. So a mirror, as you see on the right, could tilt, and that allows the satellite to look left and right outside of its what we call nadir viewing position. So this allows it to have an off-nadir imaging capability. And in fact, what this does is this reduces the spot image revisit rate from 26 days to once every 4 or 5 or 6 days. So you can see it can be flying over one place, and it could turn its mirror and scan an image off to the right or left. Very innovative, very interesting, very new technology development in the space remote sensing world. And this also gives it some very interesting capabilities that we'll mention in just a second. I want to show you a picture of the SPOT satellite data. This again is a picture taken on 9/11, and you can see very clearly this is a false color composite, and you can see very clearly not only the smoke plume coming out of the World Trade Center site, but if you look very carefully, you can see the two red hot areas of the fire right here in this location here. You can see individual boats and ships out in the New York City harbor. This is Liberty Island, where the Statue of Liberty is, that little black dot. This is Ellis Island here, the Immigration Center. This is a good example of what the SPOT satellite imagery can provide us. Because the SPOT has this tilting mirror assembly and is able to look to the right and left, it gives SPOT a very interesting capability for developing stereoscopic images. What this means is the SPOT system can look to the left and acquire a slightly off-nadir image of one area, do a couple of passes, image that same area again from the right, and these two off-nadir images of the same location, since we know the geometry of how high the satellite is, how much the image was tilted, this gives us the information to create a three-dimensional model of the surface. And so we can see on this next slide, on the right is a SPOT image draped over what we call a digital elevation model, or a DEM. This is the Grenoble area of the French Alps where the French held the Winter Olympics a few years ago. This is not a real picture. Well, I guess it's a real picture. What it is a SPOT satellite image in true color overlaid onto a digital elevation model that was created by two off-nadir pointing SPOT data sets. So very interesting capability, very useful capability, again, for creating that third dimension and for creating data that's useful in geographic information systems, or GIS, which is where most of this type of data is now being incorporated. So SPOT has some very interesting capabilities that were quite revolutionary in its day when it was first developed. We require very large telecommunications and receiving capabilities for these types of data. Very high data rates, very large amounts of data coming down when you think about 10-meter, 2.5-meter pixels. This is a picture of one of the SPOT receiving stations, a very large dish here on the left. And on the right, you see a map of all the various different receiving stations that we have around the world that can actually acquire the data in real time as the satellite is passing over that location. SPOT 4 was launched in 1998 and had a variety of new capabilities. One of the most important was the 1 kilometer pixel vegetation sensor. This is very similar to the AVHRR sensor of the NOAA satellites. SPOT 5 was launched in 2002, and it has 2.5-meter spatial resolution in the panchromatic band and 5 meters spatial resolution in the multispectral band. So a huge increase in spatial resolution since the original system in 1986. And you can see here just a couple of images of the kind of detail that we can get with this kind of spatial resolution increase. Very, very high resolution data. The vegetation scanner, as it's called, on the SPOT system, as I mentioned before, is very similar to AVHRR, 1 kilometer pixels, very wide swath width. But the interesting thing about the SPOT system is that it is co-registered with the higher resolution SPOT scanners operating on board the same satellite. And also, it operates in exactly the same spectral bands as the high-resolution SPOT data. So what you're getting is 2 different sensors at different resolutions, but that are co-registered, and if you will, the high-resolution pixels are nested within the low-resolution vegetation pixels, and that allows us to have comparability between the 2 different data sets. Here we see a picture of the vegetation imager itself in the top, and below and at the right you see 2 of these beautiful images. One of the Indian subcontinent with the Himalayas at the top. Beautiful, beautiful images, and extremely useful because of this co-registration together with the higher resolution SPOT sensors on the same satellites. The European Space Agency is also very involved in space remote sensing. Beyond the activities of the French and CNES and SPOT, the European Space Agency launched their first major space remote sensing satellite in 2002 called ENVISAT. And this is a huge satellite, monster. The joke name for it could be Battlestar Galactica, because this thing is enormous. 8 metric tons at launch, 10 meters by 25 meters when fully deployed. A total of 10 instruments, 2.2 billion euro cost, an enormous satellite. And I know many of my French colleagues were awfully nervous when this thing was about to be launched, because if they had a launch failure, they lost basically all the stuff that they were going to have for a very long time. But fortunately for them and for all of us, it had a perfect launch and was launched in February of 2002. One of the unique aspects of ENVISAT is that it is both a passive and an active system. It has the traditional passive electro-optical devices like Landsat or SPOT, but it also has a very large space imaging radar on board as well. So it's slightly unusual in that it carries both active and passive systems as well. Huge satellite, again, over 8,000 kilograms, a launch mass, has a very useful imaging radar as well as many different other kinds of sensors as well. The radar data has 30 meter pixels, very high resolution for radar, and ENVISAT is one example of a different way to do remote sensing. Instead of having many satellites, perhaps like NASA, many satellites in the same orbit following, this is where you put all your eggs in one basket and hope that everything gets up there and works. And in this case of ENVISAT, it certainly did, and it has provided a wide variety of very useful data. Another system on board ENVISAT is the MARIS. Again, somewhat similar to AVHRR, 300 meter spatial resolution, 15 bands. Very useful for things like ocean analysis, and you can see here a beautiful image of the Pillars of Hercules, the entrance into the Mediterranean Ocean, and the different sea surface temperature within that area. Here's another lovely image from Maris, medium resolution, the entire Italian peninsula and Corsica, the islands in the Mediterranean, the beautiful image of the Alps. Again, more coarse or moderate spatial resolution, but you get a much wider swath width for that. It had many different other sensors as well, microwave radiometers, altimeters, ozone measure, all kinds of stuff. And again, the benefit of this is by putting all of these things in one bus, acquiring data at the same time, we get that contemporaneity, we get the ability to acquire many different kinds of information at the same time, and that makes all of the data even more useful to us, and more we get more out of that by having those systems operating from the same bus. Spot 5 was launched in 2002, and so they're already looking for the follow-on, the next follow-on. And the French, along with the Italians and other European organizations, are looking at how can they best follow this system on. And what they're thinking about now, this could change in the future because it's still a bit early in the planning stage, but right now the next generation follow-on system for Spot is going to be what they call Orfeo, a dual-use system, again somewhat like the next generation Landsat, where it's going to combine a military and civilian payloads. Orfeo is going to be a dual-use military and civilian system, next generation system. They're planning on spending about $360 million on this. They are planning on launching 2 high-resolution optical systems called Pleiades with 0.7 meter spatial resolution. That's about 2 feet spatial resolution with a 2.8 meter color stereo, 20 kilometer swath width in 2008, and also 4 individual high-resolution radar systems, 3 meter spatial resolution radar systems, again for both military and civilian purposes. So this is the thinking right now for the follow-on for Spot 5, after Spot 5, but again, we don't know exactly whether or not this system will come together as it is planned, or indeed if it will be able to be launched at this time. So that's the French and a little bit about other European remote sensing activities. A fascinating example of the use of space remote sensing, appropriate use of space remote sensing in a developing world context is India. India has perhaps one of the best, if not the best, space program in the world in terms of applying its technologies for its specific needs and requirements. India has their own launch systems, they have their own telecommunication satellite systems, and they have their own space remote sensing systems as well. In fact, they launched their first space remote sensing satellite in 1988, just 2 years after Spot launched theirs in 1986, the IRS-1, Indian Remote Sensing Satellite number 1, a fairly Landsat comparable system, had, you can see here on the slide, 36 meter spatial resolution in the second system and 72 meters in the original, so it's roughly comparable to the Landsat MSS and thematic mapper. In 1994, they launched the next generation with 23 meters. They launched a radar system with a 25 meter spatial resolution. India has a very, very active space remote sensing program, and is very focused on meeting India's specific requirements in terms of agriculture, environment, and economic development. It's focused very much on developing technologies, not for technology's sake by itself, but developing technologies to assist India in the specific kinds of development issues that they face. Here's a beautiful image of some of the Indian data that we can see. This is a 5-meter satellite image on the right, which is the area just around Washington, D.C. You can see very clearly Washington, the rivers, the bridges across, 5-meter data, very high spatial resolution. In the left, the color image is a 5-meter data set merged together with a color Landsat 30-meter image. So we're getting the color, the spectral data, if you will, from the Landsat and the high-resolution spatial data of the Indian remote sensing satellite at 5 meters. Very high-resolution data. The Indian systems are excellent. They work extremely well, very high-quality data, and here's a fascinating image. I actually grew up in Oklahoma City, just outside of Oklahoma City, Oklahoma, a little place called Midwest City, just outside of Tinker Air Force Base, a large U.S. Air Force base. And in fact, you can see the runways of Tinker Air Force Base here in the upper right portion of this image. In this image, you can actually see the path of the huge major tornado that struck the Oklahoma City area just a few years ago. And the path of this is this light area that you can see here. This image was taken only a couple of days after the tornado passed, moving in this direction. And you can see the lighter area is essentially the part of the earth that was scrubbed clean of vegetation and everything else. And you can also see that this tornado was headed straight for Tinker Air Force Base, and it just turned away at the very last minute. But this is an excellent example of the kind of data that can be acquired from these satellites and the amazing things that they can show us about our planet Earth. India has also launched a wide-angle, low spatial resolution sensor called WIFS. This is a 180-meter spatial resolution, very wide swath width, and again, here's just an example of the kind of information that we can see in this. And here's a lot of snow cover here. This image was taken in the winter over North America, and you can see the snow cover up in the northern areas, some clouds off of the Chesapeake Bay. Again, very comparable to the vegetation sensor of SPOT or the AVHRR or MODIS of the United States. India continues to develop its remote sensing technology. Very active program. They launched a research satellite in 2001 with a 1-meter spatial resolution. 2003 they launched ResourceSat that has an improved 23 spatial resolution multispectral system. 2005 saw the launch of a CartoSat, a satellite specifically to do cartographic mapping at the 1 to 50,000, 1 to 25,000 scale. 2 stereo pan imagers, somewhat comparable to SPOT, capable of generating ortho images, these digital elevation models that I showed with the SPOT data of Grenoble, and to generate high precision georeferencing for cartographic mapping products. Very advanced satellite, but also very functionally focused. It's focused on meeting needs that India has in terms of meeting its mapping requirements. OceanSat is the next one, again, oceanographic satellite, very advanced technology, and again, very focused specifically on meeting the needs of the Indian people. China and Brazil have joined together to launch 2 satellites called CBEARS, the China-Brazil Environmental Remote Sensing Satellite. In Chinese, it's called Ji1. This is a joint project between INPE, the Brazilian Space Agency, and the Chinese Academy of Space Technology. INPE developed the sensors and the satellite, and the Chinese launched it. 20-meter multispectral data, 5 bands, a 80-meter panchromatic and far infrared. Wide field imager, again, comparable to AVHRR or CWIFs. Both satellites launched and operated just fine, extremely well. An interesting technology transfer activity. The Chinese had the launch capability and very much wanted to gain additional capability in advanced space remote sensing systems. The Brazilians had the technology for the satellite sensor itself and more satellite bus technologies, so they joined together. Each have learned important things from the others, and it's provided very useful data for both, and also, importantly, useful learning as well. The Chinese continued to develop their remote sensing capabilities. In 2004, they launched the next generation of the Ji1 family. It's a new system, a follow-on system, different from the CBEARS. I regret I don't have a great deal of information about this. The only picture of it I could find is this pretty first release stamp showing the satellite bus. So I'm sorry, I don't know very much in terms of specifics about this second generation Chinese digital remote sensing satellite system, but we will certainly be learning more about it as we go on in the future. Again, somewhat similar to India's practical application, China is in the process of developing their own disaster mitigation and warning satellite constellation. This is a fairly new development. They are looking at establishing their own internal constellation of satellites specifically for use for disaster mitigation and response. China is an enormous nation. 200 million people in China a year are affected by natural disasters. And this is having an enormous human and economic effect on China. And so they have decided to develop a 6-year plan to develop 6 dedicated satellites to be used for natural disaster mitigation and monitoring. I don't know too much about this at this point, other than they say it's going to have less than 30 meter spatial resolution and be a combined optical and radar system as well. So we'll have to see what happens with this system as it is launched and developed. The Republic of China and Taiwan also has a space remote sensing capability. They had the French build and launch ROCSAT in 1999. 5-meter panchromatic, 15-meter multispectral, stereo capability. A second follow-on system with even higher spatial resolution, 2 meters, 8 meters. It was renamed Formosa. And you can see one of the images taken from it. So again, many different countries are getting involved in space remote sensing. Perhaps nations that you may not have thought were operating their own space remote sensing satellites. A very active nation in space remote sensing is Japan. Japan has been involved in space remote sensing since 1987. Again, just 1 year after the French launched Spot. They have a very active remote sensing program. They've launched satellites essentially every couple of years. They have a variety of different kinds of satellites, active and passive, various different spatial resolutions. and they have had a great deal of success and some failures. ADOS was their Advanced Earth Observation Satellite, very large, complex satellite, very capable, but unfortunately it had a failure early in its life, and that's one of the dangers you have of building these large, complex satellites. If you lose them, you lose pretty much everything. It had an 8-meter panchromatic image. Here we see the panchromatic image of the Hiroshima prefecture, and a 16-meter multispectral image capability as well. Very advanced technology design. The Japanese are very involved in space remote sensing for many reasons. Their latest is called ALOS, the Advanced Land Observation Satellite. It's scheduled to be launched in 2006. It's a 4,000 kilogram satellite, and again has a wide variety of different systems, somewhat perhaps like InVSat, in that it has a combination of a radar and high resolution and moderate resolution optical systems as well. So I hope you can see that we have many, many, many different kinds of space remote sensing systems. And if this lecture started to get a little bit redundant, there's a good reason for that, because an awful lot of these things look alike. They have similar characteristics, they have similar capabilities. And so some of the questions that arise from this is, why do we need so many of these satellites? Why do we have so many of these satellites that function the same? If we look at this next slide, you can see again, we showed this before, many of these satellites clump together in comparable groups. Down in the bottom left, we have the extremely high resolution systems that we're going to talk about in a further lecture. We have all these Landsat-like systems, we have radar systems, we have these wide area imaging systems. And what's interesting is, as I've showed you this slide before, essentially they're very, very similar. They're similar in characteristics, they're similar in orbits, they're similar in their data rates, they're similar in all of their spectral and spatial and radiometric characteristics. And so the question has to be, why are there so many of these systems? Why do they look so similar? And why are we spending billions, literally billions of dollars worldwide to develop and operate all of these systems when they essentially are redundant? And there are many reasons for this. One of the basic reasons is, of course, national pride. Space technology still has a certain panache to it, and for a country to be able to develop and operate and launch their own satellites has an element of national pride to it. But I think a larger question is also economic. There is a market for space remote sensing. People want to be a part of that market. They want to, they would much rather use their own satellites and their own satellite imagery rather than pay someone else from another country to utilize their systems. But I really think the real answer to why we have so many, if you will, redundant space remote sensing systems is the dual use nature of all of these systems. And by dual use, of course, I mean that they have civilian and military applications. All of these satellites and the data they derive have potential military uses. And the higher we go in spatial resolution, the smaller an object that we can see on the ground, the more military application that we have with these data. So I think the real use or the real reason why we see so many of these systems being developed concurrently is the fact that each of these nations around the world want to have their own native capabilities to develop and operate these satellite systems. So yes, they want to do environmental analysis, they want to look at forests and land cover and agriculture, they want to do disaster management, but in the end also that military capability really is very important. They want to be able to look at the countries near them with their own indigenous capabilities. They don't want anybody to be able to turn that satellite off in time of crisis. And so I think that's a major reason why we see so many concurrent satellites being developed. So, again, I want to thank you very much for joining me in this series. I hope you're finding it interesting. I'm certainly enjoying presenting this material to you. And now look forward to seeing you in our next segment. Thank you.